structures quiz. You start off with, this is the nitrate ion, NO3, 1 minus. And if you do the Gooch math, then you quickly count up your valence electrons. We've got 5 coming in, we've got 6 times 3 coming in, so we have 18 plus 5, 23. And because this has an extra electron, it's got 24 valence, and I'm doing this really sort of fast and dirty. 24 valence, and if everybody was satisfied, and I'll take my other little shortcut of saying, well, everybody wants 8, we have 4 of them, octet is 32. So shared is 32 minus 24, or 8 shared, and we have, that means, whoops, divided by 2 means 4 bonds. And how many unshared pairs do we have? Well, we have 24 and we're sharing 8, so we have 16 unshared. Okay, so the only way to put 4 bonds, obviously we know nitrogen is going to go in the middle. It's not only less electronegative, but it, by golly, it's the only one of its kind. So if we start off with single bonds, that gives us 3. We know we're going to have a double bond someplace. So I'm going to cheat and copy this because we can do this with the iPad. Oops. Let me shrink all of this stuff. So we have to draw that double bond every place that it could possibly exist, which is all 3 of those locations. That's called resonance, because we don't really know where the double bond is. And then we have to put in those 16 unshared electrons. So to satisfy octet, the nitrogen is satisfied. 2, 4, 6, 8. Nitrogen can't accept any unshared electrons. The 2 oxygens that only have single bonds are only feeling like they have 2 electrons, so they need 6 more to complete octet. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That gets us up to 12 unshared. We have 16. To fill an octet, the one that has a double needs 4 more electrons. So that gives us what we need. We have to bracket it and put up the charge because, of course, it's an ion. And we have to put that double-headed arrow in there. So then we're just going to go through and do the same on each of these. If they only have 1 bond, they get 6 electrons. If they have 2 bonds, and I just did a very bad job drawing those, they get 4. And we have to put the brackets in the charge. Okay. Good on that? And that nitrate, for some reason, seems tricky, but it's really not. Especially once you use the Gooch math, I think the nitrate is really, really simple. Okay, let's do SO2. So this is sulfur dioxide. It's a nice covalently bound compound. So we have SO2. Sulfur coming in with 6, oxygen coming in with 6 times 2. We have 18 valence. If everybody was happy, 8 times 3, we would have 24 octet. So 24 minus the 18 valence, we get 6. Shared divided by 2 gives us 3 bonds. So if we have 3 bonds, and we only have 3 things, well, if we hook it together with single bonds first, we know we're going to have to put a double bond in there someplace, and I'm going to, again, cheat and copy this. Okay. So we know that there will have to be a double bond. We know we have to draw it in each place that it can exist. Now, how many unshared electrons do we have? So we have 18, and we're sharing 6. That means we have 12 unshared. And if we look at our octets, you know, again, oxygen that's double bonded only can accept 4 more electrons. Oxygen that's single bonded can have 6 more. So that gets us 10. We need 2 more. Is the sulfur here satisfied from an octet perspective? No. It needs 2 more. So we're just going to go through and do the same thing over here for that. And this, oops, this is not an ion, so it does not get brackets, but it does have a resonance structure, so we do have to draw that. So we put that in, and we've got it. Okay, good. Move along. Okay. So our next one is an organic compound. Remember we talked a little bit about ethanol and functional groups. This is methane, CH4, but instead of one of the hydrogens, we put in a chlorine atom. And this is really common if you take organic chemistry. You do chlorination and bromination reactions, where organic chemicals will sort of accept a halogen in place of a hydrogen. So pretty common. So this is CH3, whoops, Cl. So we've got 1 carbon, 3 hydrogens, and a chlorine. If we go through and do the Gooch math, carbon's coming in with 4, chlorine with 7, hydrogen with 1, times 1, times 1, times 3. So 14 valence. If everybody was satisfied from an octet perspective, carbon and chlorine both want 8. There are 2 of them. Hydrogen wants 2. There are 3 of them. So 8 and 6. Whoa, wait. 16 and 6. Let's try that, shall we? 16 and 6. So we have 22 octet. 22 minus 14. 8. 8 shared divided by 2. 4 bonds. If they're sharing 8 and they have 14, they have 6 unshared. So we know carbon is central. If there is carbon, we have 3 hydrogens, and we have 1 chlorine. We only have 4 bonds. 1, 2, 3, 4. Cool. We have 6 unshared, and hydrogen satisfied, carbon is satisfied, chlorine came into this with a bunch of unshareds, and it keeps them. And there's no resonance, and there's no charge, so pretty easy. C2H4, we have 2 carbons, 1 hydrogen, or 4 hydrogens. 1 times 4, 4 times 2, 8 and 4, we have 12 valence. If everyone was happy from an octet perspective, we would have 16 plus 8. So octet equals, wait, that can't be. 8 times 2, 16. 2 times, yeah, okay. 2 times 4. 8, 16, 24. Thanks. So the octet is 24 minus the 12 that are existing. We're actually going to share 8. Oh, yeah, okay. Which means we have 4 bonds, and we have 4 unshared? No.
It should be 12. Yeah, 4 minus 12 is 12.
Oh, gosh. Yes, it is. Thank you. I'm like, that's not right. I know that's not right. So we have 6 bonds. That's better. Okay, we've got 6 bonds. And we have 12 shared, 12 valence. There are no unshared. So we've got carbon, and carbon attaches to carbon frequently. And these hydrogens can only attach to one other thing, so hydrogen can never be central. And we know we've got 4 hydrogens, so first off, we would try just sticking them in like that. Well, that gives us 2 4 bonds. We need 6 bonds, so we still need 2 bonds. Is there anything here that can double bond? Carbon. So that's a double bonded carbon. So it's a ethene, yeah, there are naming conventions in organic chemistry for things that have double and triple bonds. Anyway, so you get that. I'll tell you what, just to speed this process along, for the next 3, I'm just going to draw the structure. And if you have further questions, pop in and we'll talk. Okay. So we've got SO4 2 minus. When you do the Gooch math, it works out to having 4 bonds. It works out to having 6 times 4, 24 unshared electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Badly drawn.
No.
6 times 4. I was cheating because I know how many there are without doing the Gooch math. Because I know that every oxygen is going to have 6. And because it's an ion, of course, we have to bracket it. We have to write that formal charge. Ammonium, the ammonium ion. You will get so familiar with the ammonium ion in the next chapter. When you do the Gooch math, it works out that there are 4 bonds and no unshared pairs. And this whole thing altogether has given up an electron, so it overall has a 1 plus charge. You get really accustomed to using this one. Okay, and then our last one, ammonia. If you have cleaned with household ammonia, you are familiar with this. That's all it is. So we have N. If we do the Gooch math, it works out to 3 bonds and 2 unshared electrons. And that gives us something like that. So you can kind of see when you go back and forth from ammonia to the ammonium ion, one of these goes off into space and another hydrogen comes in there and bonds, and that's how you go from there to there. It's kind of cool to see those two right after the other. Okay, so let's now start to talk about geometry. Well, first of all, questions on this. The substances that were on this quiz, these guys, all conform to the rules for octets. They all end up satisfied. Hydrogen obviously doesn't conform, but hydrogen is just an octet exception. We know about it. What we'll do soon are what are called expanded valence, and I forget the term for the other one. It's basically ones where they don't fill up. They don't fill up an octet, and they're okay with that. So we'll start doing those weirdos as we do molecular geometry. Ooh. So, geometry, molecular geometry. You know that geometry means the shape of things? Molecular geometry. Can we talk about ionic compounds in molecular geometry? Why not? Show me a molecule of an ionic compound. Gesundheit. Gesundheit. Do ionic compounds form molecules? No. Salt, that giant chunk of salt that I have up there, there are no molecules of salt. There has never been a molecule of salt. There's an ionic solid. But they're not forming discrete independent molecules. So when we talk about molecular geometry, we're going to start to talk about the actual shape of individual molecules. This is all covalently bound, substances. Okay, and we can talk about molecular geometry for both polar and nonpolar substances, but it's all going to be covalent. So we talked a little bit about why the forces of attraction within an ionic compound or the forces of attraction within a metal in the giant mosh pit of electrons. I so love that now. Why that influences their characteristics. And to, and I want to say to somewhat a lesser degree, but how the atoms are actually arranged inside a molecule also changes their characteristics somewhat. It definitely changes their shape. but when we get into things that are polar because they have unshared pairs, then there's water behaves the way water does largely because of those unshared pairs and the fact that it's polar. It's like polar plus. So again, that profoundly weird thing that the world around us behaves the way it does because of how the atoms are arranged. That's going to leave me like looking at a rock at midnight, thinking, it used to be 2 a.m. I'm too old for that stuff. Thinking, man, I can't melt this because of the atoms in it. Wow. Huh. When molecular polarity is one of the big things that changes how things behave. And this is where we talked about polar molecules. So uneven distributions of charge on molecules. Water is a big one. How many of you have ever floated? How many of you have seen water striders? People call them water spiders, but they're not spiders. They're 6-legged insects, and they skim across the top of the creek or the pond, and they're really cool, and they look like the little ice skaters. They're moving on liquid. How do they manage to move on liquid? Magic. We can't invoke the supernatural. No magic. Science. We have to use natural explanations. How can they move on water like that? Crazy little things. How? No. That was a good try. No. It's surface tension. Water actually has a skin. There is surface tension on water. You have experienced surface tension if you've ever done a belly smack. You ever done a belly smack? Yeah, you hit that water. It feels a lot like a solid, doesn't it? It stings. You've just hit the surface tension. And surface tension happens in water because at the surface of any kind of water, what we have are all those little Mickeys lined up and gripping one another. And the little positives line up with the little negatives, and there are actually, because of that area of partial charge, positive, negative, positive, negative, positive, negative, whoops. You're actually getting this sort of connected skin. So it behaves a little bit like it was a surface because there are actually forces of attraction holding those molecules together. You have to use some energy to overcome that surface tension. The energy that you feel when you belly smack is, of course, the force of you breaking through that. But that's what molecular polarity can do for you. It also makes paper towels possible. Did you know that? Why does a paper towel suck up water? Because you have a property of water called capillarity. Do you know what capillaries are in your body? What are they? They are the tiniest blood vessels in your body. They are about 1 red blood cell in diameter. And capillary action is the tendency of water to climb very skinny tubes all on its own. They have little tiny things called capillary tubes. If you've gotten a finger stick for a blood test, and they sometimes take a little glass tube and they stick it right on top, and the blood goes whoop, up the tube. Have you seen this? It's a capillary tube. I used to have a collection of them. I don't know where they are. Water does that because it is water's only attracted to 2 things in the entire universe. Have I told you this before?
Yeah.
Itself and everything else. And somewhere I have a great chemistry cartoon of that a student drew me years ago. When you put water in a narrow little tube, let me get rid of that for a second. This water molecule is attracted to the side of the tube, and it clings. And it goes up, and then it's also attracted to the water molecule behind it, so it pulls its little buddy up. And then it's attracted a little bit higher, and it pulls its little buddy up. And so this water will actually climb up to a point, and there comes a point where it can't overcome gravity. But all a paper towel is a fibrous cloth with lots of little tubes out of the fibers. And those little tubes are what enable a paper towel to suck up water, because it's just performing capillary action. So it's because of that property of water. It's because water is attracted to itself and everything else, because it's both cohesive and adhesive. That capillary action enables little water molecules to travel through. Same reason your T-shirt will wick up water. If you get the edge of your T-shirt wet, the wet will spread. It's capillary action. It's because water is a molecular compound. It's because of the molecular geometry of water that is possible. I think that's amazing. So, when we go to actually figure out the geometry of any given molecule, there's model making that goes into it. There's some testing that goes into it. Part of our model making when we do this is mathematical modeling. The Gooch math is mathematical modeling. We're figuring out, well, based on the math, how many shared electrons should there be? How many bonds should there be? That's making a mathematical model. When we do a Lewis structure, we are making a visual model. We're drawing it. In this chapter, we're also going to start making physical models. And this is what your molecular geometry lab will involve starting on Tuesday. So you're going to get a list of molecules, and you're going to, for each of them, do the Gooch math, for the ones that allow Gooch math, draw the Lewis structure, and build a physical model. And there are some ways that we classify these physical models here. I just threw water at Caitlin, and she didn't even get wet. So you can pass that around. But we're going to, for each of these, look at a physical model. What's neat these days is that we have tools in chemistry to actually visualize the shape of molecules that, 30 years ago, 20 years ago, we didn't have. So the model making was all theoretical. It was all based on the math. And what is great about science is that it's predictive. So there are a lot of things where there were predicted models for given molecules, and now we've had the technology to visualize those molecules. There is one that you may be familiar with. Did any of you see Photo 51, The Secret History of the DNA Molecule in Biology? Okay. If you haven't seen it, I would say you should watch it on your own. It's probably available for free someplace online. It's a PBS Nova, and it's about the race to figure out the shape of something that you all take for granted. You all learned what a DNA molecule looks like in science, right? Duh, yeah. We didn't know that prior to the 1950s. It was unknown what shape this molecule had. And there were people who were building theoretical models based on some characteristics of this molecule. And there was one woman, Rosalind Franklin, who really got shafted. She got the short shrift. Well, no, you know what? In defense of the Nobel Committee, they do not give posthumous Nobels. So if you die before the project that you worked on receives a Nobel Prize, you are not listed. But in her lifetime, the lady got the short end of the stick again and again and again and again and again. She just got cheated. She did. She did. Now, and when we get into some of this, we'll talk about, the kind of math she was doing, and I think I'll try to show a few little short clips from it, because I think as you do this model building, you'll start to be able to appreciate the kind of intensity of the model building that she was doing with not a lot of data. What she was using for data to extrapolate from looks like pretty thin soup to us, but she was pretty brilliant. She was pretty awesome. But anyway, okay, so we're going to go through molecular geometry. So there are some terms and some sort of generalities about molecular geometry you need to be aware of before you start model building. The first thing to talk about is what's called Vesper theory. And if you ever went to camp and you had Vespers in the evening, this ain't them. 4-H camp, they used to take us out on the covered bridge over the creek and listen to the sounds of nature in the evening. And it's really a way to get a bunch of 14-year-olds to calm down after dinner and socialization. But it works. So this is not those Vespers. And yes, it's not really spelled Vesper, but that's how we all say it. It's valence shell electron pair repulsion theory. Woo! So this is kind of like the Ballad of Cutie Pie and Best Friend. It's all about attraction and repulsion. Opposite charges want to be side by side. Like charges, I'll take the water back, thanks. Like charges don't want to be anywhere near one another. So you have sets of electrons, and if you've got, and I'm going to draw this in the fake way, meaning you know that orbitals are just areas of high probability, but I'm going to draw them like little balloons. You know, if I've got a little balloon here, I should draw the boundary of that smaller, with 2 electrons in it, and I have a little balloon here with 2 electrons in it, those 2 little balloons want to be as far apart from one another as possible. They are repelled by one another. There is a strong force of repulsion between them because they have like charges. Now, similarly, if I have, I'll draw a little hydrogen nucleus here. So if I have a little hydrogen nucleus here, and I have a little hydrogen nucleus here, that wants to be as far apart from another hydrogen nucleus as possible because there is a powerful force of repulsion between them. Don't even try to copy that arrow. It's really stupid and I shouldn't have drawn it like that. Okay. Repulsion. They're repulsed by one another. So everything about how, and are you noticing a trend here? Like with bonding, we talked about how they will bond at a point where repulsion is minimized and attraction is maximized. Guess what? It's the same thing for this. So that bond length thing that we discussed, where the bond is going to form where you've got minimum repulsion and maximum attraction, that's how they're going to settle out geometrically too. So it all comes down to these forces of attraction and repulsion. Okay. So because of the fact that these things are repelling one another and getting as far apart from other nuclei and from other electron orbitals as possible, what that means is that if you just have 2 things, the farthest they can be apart from one another is a straight line. And that's what they're going to do. If you've got 3 atoms, they're going to do the same thing. They're going to be in a straight line from one another because that's as far apart as they can get. If you have 4 atoms, and this is like our NO3, our nitrate ion, the farthest they can get apart from one another is on a flat plane out at the points of an equilateral triangle. And we call this, because, you know, chemistry people so creative, trigonal planar. It's all in one plane, and it's a triangle. And then we have this wonderful thing called tetrahedral. You remember the cow fart I showed you earlier? Our little methane molecule? Well, our little methane molecule happens to be tetrahedral. I will pass this around. Because the farthest that these things, and please disregard the color of the bonds, I rather screwed that up. This is my tetrahedral. The farthest these things can get apart from one another is not on a single plane. And I'm going to throw you a cow fart. Good touch. So the farthest they can get apart from one another is actually, does anybody know what a caltrop is? See, I think to broaden your education. These things look like a caltrop. It's a medieval anti-cavalry weapon that's basically 2 spikes. Like imagine a nail with 2 points, no back end to hammer on. It's like 2 nails welded together, so no matter how you throw it, there's always one sharp point sticking up. And at one point in battle history, these would be thrown out in front of approaching armies, injuring the horses' feet so that they couldn't continue marching. They've been used against vehicles with puncturable tires. So that looks like a caltrop. No matter how you throw that methane molecule, 1 point's going to land up. 1 hydrogen is going to land up. Where are my caltrops? So that's because those things want to get as far apart from one another as possible. And that's the driving force in figuring out these geometries. How far apart can these things get and be equidistant? Now, here's the interesting thing. Where'd my water go? So, there are some molecules that have not only atoms attached to the central atom, but they have unshared pairs attached. And this water molecule is an example. That oxygen that's central has 2 unshared pairs. Well, here's the thing. Those behave just like there was another atom attached there. So these things push the hydrogen nuclei, which also have electron cloud around them, they push that valence shell on the hydrogen down. So instead of, you look at this and it's got, well, you've got 3 atoms. Shouldn't it be linear? No. What we get are these weird geometries. This one is called bent. Can you see why it's called bent? It looks bent. This geometry is identical to this geometry, except in place of 2 atomic nuclei that we can see, in place of 2 hydrogen, what we have are 2 unshared pairs. So it looks like there's this ghostly hand pushing those hydrogens down, because if you don't visualize those unshared pairs, you don't understand why these little hydrogens aren't out in a straight line. Why don't they look like that? Because they're being affected by the unshared pairs. So typically we have what are called, we have bent. If we had an unshared pair, ouch, here. So this has only got 3 things attached, right? We would think it might be trigonal planar. 3 things attached to a central atom. But it's got an unshared pair here, which pushes all of these hydrogens down. And what we end up with is something that's called pyramidal, because this looks like a little pyramid. Here's the point of the pyramid. Here are the bottom of the sides of the pyramid. Okay? Oops. So we have these odd geometries because we have unshared pairs that are changing the geometry of these molecules. What I'm going to do is hand out the lab, or I'll have you pick up the lab right before you leave. What we'll probably do is we'll talk a little bit more. We're going to talk about hybridization on Tuesday. So you'll have most of the period to start working on the molecular geometry lab, and then we will pick up with hybridization.